welcome everybody this afternoon to our NFDI4Chem Stammtisch. Today we want to talk about our efforts to make NMR data fair, what we are doing in the NFDI4Chem context, and I will briefly start with an outline. We will, of course, introduce NFDI and NFDI4Chem very shortly because most of you will at least have heard of it. We will see what the status quo in NMR data management is today and what we want to change and how we want to do that, and show you some activities in NFDI4Chem, and at the end, of course, we want to discuss with you. So let's get started. What is NFDI? What is NFDI4Chem? NFDI is the Nationale Forschungsdateninfrastruktur, or English National Research Data Infrastructure, which is a initiative funded by German federal and state governments and covers a lot of scientific disciplines in order to establish modern research data management. NFDI4Chem is the chemistry consortium in the NFDI. Our vision is to make the data lifecycle complete, which means that if we have any experimental data, from the design of the experiment over data, the experiment conduction, the data collection, processing, analysis, publication, the cycle gets closed in the end by reusing the data. And this is, of course, a special challenge for NMR, as you will now see, because as we see in this famous painting by Magritte, we see very nicely what the problem with NMR data usually is today, that most of the NMR spectra available, for example, in supporting informations or in other contexts of publications, are not really data. They are just like this pipe, not really a pipe, but a representation of a pipe, and this is also applies for the NMR spectrum. This is no data, this is just a coarse picture of data. So this means the data is not fair in the sense of being fair, being findable, accessible, interoperable, and reusable. And especially concerning NMR, this means findable means that the data set should be reachable by an identifier, for example, a DOI. It should be accessible in terms of that it's deposited in a repository that is accessible. It has to be interoperable, which means it has to have machine-readable data and metadata so that the data can be used in different contexts, and of course reusable, mostly concerns with license questions. So for NMR, this looks like this. We have more or less the same stations, of course, in the life cycle, but we will now focus on this life cycle, especially in the context of NMR. And when we see when we compare the ideal world with the actual world today, we will see that the life cycle is mostly interrupted at two stages between the analysis and publication or disclosure, and then thereon from the publication to the reuse. And these two stop sign or single way lane sign, whatever, stem from the publication of NMR data is not fair because it's based on UPAC recommendations from the 1970s, which came from a time when NMR, of course, was electronically recorded, but still, in the end, we had analog plots. There was no computer storage, no computer analysis of NMR data, and this is the state of the art that is reflected in the recommendations, which more or less persist until today. And because of that, so this does not allow to publish NMR data fairly based on the current recommendations. And this also hampers, of course, the reuse of NMR data, because if the published data are not fair, then of course the reuse is extremely difficult. So where do we want to go and why? Of course, this is our ideal world. And why is it so important? Of course, machine learning, artificial intelligence becomes more and more important also in the science world. we see that artificial intelligence has a great potential at assisting research and science. And of course, all of this is only possible when data is interoperable. So interoperability is actually a major requirement for using data in artificial intelligence applications. And this is a major challenge when it comes to NMR data based on standards of the 1970s. Also, we want better NMR prediction. NMR prediction is, of course, possible on quantum mechanical level. However, this has little practical relevance. It's very precise to an extent of precision that is not practically relevant. And on the other side, it's extremely slow. It takes some hours to make a calculation, which means that NMR prediction is normally empirical because this is blazingly fast. And actually in NMR prediction, machine learning in the terms of neuronal networks is already a thing since the 1990s. So it's artificial intelligence is actually not new to NMR. So the prediction is very fast, very efficient, but only as good as the underlying data. So if you have unknown compound classes, in the organic chemistry, it may be a new ring scaffold that was not known before, but it's even more interesting when you have inorganic compounds with heteronuclei and complex binding situations. Of course, the prediction will fail because it has no data to root on. So what we imagine is the future that we have a lot more high-quality standardized data to make machine learning models more robust, more efficient, that they are ideally, if we are lucky someday, we are maybe so lucky that they become robust that they even can make some sort of educated guess about unknown compounds. But this is, of course, very utopic at the moment. What has already been done, we're going to history here, and we want to start with briefly considering what is NMR data actually. Of course, you have a sample, you put it in the magnet, you get raw data from the NMR spectrometer, which is 1D and 2D spectra. The data will then be processed and ideally in the end assigned. And so we have different types of metadata. The raw data will, of course, have all the technical metadata, what experiment was used, pulse sequence, the probe head, the frequency, delays, whatever. And you have the assignment data, where the metadata is the molecular formula, chemical shifts, coupling constants. And what is something interesting about NMR data, in my opinion, is that at the level of the assignment, data and metadata is actually very hard to distinguish, because an assignment, depending on the point of view, you could consider an assignment either data or metadata. It gets blurry at this point, and this is a challenge for standards and data formats. And so when we go back in history to the 90s, we see JChem DX, which until today is the only really accepted free format. If you look at this, you see that well, it's somewhat easy to read for humans, but it's well, it's very old. And of course, it has, I mean, it obviously has some advantages, because otherwise it would not exist anymore. It is open and very common because the recommendations from the 1990s exist. There's a lot of data in this format already available, but the format is very outdated. It does not officially support 2D NMR, and in terms of technical terms, it's not really state of the art anymore. This string-based annotation of metadata would not be done like this anymore. So it's also technically not very efficient. It's also no longer maintained. And because of the missing 2D support and other features, which at some point became important, the vendors started implementing these on their own, which means today we have vendor dialects which do not necessarily have to be compatible to each other. So the takeaway message from this would be, it's not perfect, but currently the best option available. because we have been in discussions about new data formats for a long time, and we always noticed it is an open NMR data format is a very complex matter, and not only to develop a format, but to make sure that it covers every aspect of NMR and is also accepted by the community is an incredibly difficult task. So we will probably stick to JChemDX for some time longer. What is already existing? NMR ShiftDB. I think last year NMR ShiftDB had its 20th birthday. It goes back to a project of a person you may know, Christoph Steinbeck, and it was the first open community NMR database, which assembled compounds and shift assignments, and today it has 68,000 experimental spectra with shift assignment. So until now, this is a remarkable figure for a community project with no commercial interest at all. And this is also this also explains why the prediction quality of NMR ShiftDB, despite of the sometimes awkward user interface, is still really, really good for organic compounds. I also want to mention the projects of Luc Patigny, who started with, came into the scene with nmrdb.org, which a little bit confusing, was not so much a database, but more a suite of prediction and visualization tools. And this also exists for, I think, like 20 years. It was an open source NMR simulator and web-based spin system simulation, which was also quite ahead of its time when it started. So next topic, what do we offer? And I hand over to John now.
So I'm going to talk to you about some of the practical solutions that we have that you can use in the lab in your everyday work. So starting with basically collecting the data, analyzing your data, and storing it. So basically what you're doing up until publication. We have an ELN within the NFDI4Chem project, which is called Chemotion, but it's not just an ELN, it's also linked to an open access repository. For you that are not familiar with Chemotion, it was initially developed at KIT, and the people who developed the system are now part of the NFDI4Chem consortium. It was originally in ELN, developed for synthetic chemistry, and it has since been applied to other chemistry subdisciplines, and we are working very hard in making it more applicable to other scientific disciplines as a whole. And the key focus of Chemotion is actually realizing the fair data principles. That really lies within its DNA. It's open source and it's free, so you don't have to pay for anything. From a user point of view, it's operating system agnostic, it's browser based, and basically it is a holistic solution to research data management, because the analytical devices can feed data directly into the ELN, so you have direct device integration. You can even set it up that it can convert it to open formats, and then if you want to publish your data, there's a direct link from the ELN to the repository where you can publish your data. So here's an example of the device integration. You can see on the left there's the user's inbox. They're just dragging and dropping the data across, and then they have the data in the ELN themselves, right? So they don't need to worry about any manual uploading or whatever. They get the data directly from the device and it lands in their inbox. So it's very, very friendly from the user point of view. If the users want to analyze data in the ELN, there are a couple of ways that you can go about it. So in the ELN, there's the spectra editor called ChemSpectra. It's not just for NMR. It's in principle, it can deal with many different types of data. So it can do 1D NMR, infrared, HPLC, UV-Vis, mass spec, cyclic voltammetry, and all the other methods that you can see listed on the slide here. It's first and foremost a spectra editor for JCAP, but it can also deal with additional file types as well. So when it comes to NMR, it can actually deal with the Bruker files directly. Here's an example of how it's used. It's accessed directly from the ELN itself. So the users don't have to open an additional program. They just click on the spectrum within the ELN interface, and then they can get cracking with their analysis. There is another way the users can analyze NMR data in the ELN using NMRium. NMRium is considerably more sophisticated when it comes to NMR analysis, with respect to chem spectra, and actually the users can do 2D analysis as well. And since NMRium is a project that Johannes has been working on himself and he's quite passionate about, I'll hand the word back to him briefly to talk a little bit about NMRium.
Yeah, thank you. I'm actually, NMRium is one of the most exciting things that happened in open source and NMR or digital NMR spectroscopy over the past few years, because it has become a very complete open source browser-based solution for handling NMR data, which means displaying and analyzing them. The original genius behind NMRium is Luc Patini. I previously mentioned him with the NMRDB and the visualization of spin systems. So this NMRDB.org is practically the parent of NMRium. It's developed by Luc's company, Sarcodium, but we are, of course, closely collaborating with him because this is really a centerpiece in our NMR or fair NMR strategy. I want to show some highlights about NMRium. So NMRium allows you to visualize, of course, 1D spectra. You can easily browse through them with your mouse. You can use the mouse wheel to go up and down with the level. So it's pretty much like the NMR tool you are used to. You can also see, you can also visualize 2D spectra and you can analyze them. And all of this happens in your browser. You don't have to install any software. It's completely free. And many people also confirm that it's really easy to use once you get the hang on a few basic using concepts. Another highlight, I mean, it's had, NMRium has some more features to offer, but we will go on the features which are most important for fair data. We have an automatic multiplet analysis, which works very neatly. Of course, you can also edit the multiplets manually, but this is something that really saves you time when analyzing NMR spectra. That, as you can see, the multiplet analysis is pretty much one click. You have the integrals, you have the multiplicities, then you can go on assigning, which is the next slide. So once you have your multiplets and you have a structure, you can just pop the structure in your spectrum, go on the multiplet and assign the resonances. And this is, I think, a very easy way to provide electronic assignments. And with a further integration of NMRium with the other tools John and I are presenting today, and especially Chemotion, this will really make publishing assigned NMR spectra a lot easier. Of course, for the data publication, we have to lay some groundwork because, as I mentioned before, we need metadata. Metadata is extremely important, obviously. And metadata does not only have to be human readable, it has to be machine readable. And this is where minimum information and terminology or ontology come into place. So we are also working on a minimum information standard for NMR. You can see a sample of this. This is actually mostly a table, but in this table is a lot of discussion work. What is the information that is really required for NMR spectra to be reusable and to be interoperable? And what is still useful to understand the data set? And this is closely linked to ontology or terminology, which means that for the metadata items, you have machine readable terms. So this is these letters and numbers here. These are identifiers for the ontology terms. And this is really important because this is what actually allows computers to understand the data. If you want advanced machine learning or artificial intelligence models, the computers have to learn what the data mean, and this is what the terminology is for. So for the long-term interoperability, this would be the take-home message here. We need this thing, even if it's very technical and probably very dry for the average chemist. So at this point, I hand over to John for the final round.
So Johannes just briefly talked about how and what to publish. Now I'd like to talk to you a little bit about where you can publish your NMR data. So we briefly already mentioned that Chemotion has its own repository where data can be published. So this can be data concerning reactions, samples, but also analytical data, and this also applies to NMR data. Some brief facts about the Chemotion repository. It's hosted in Karlsruhe. You can actually interact with the data directly in the browser, and it's actually now a recommended repository by Angewandte Chemie. Here you can see what it looks like. Every sample gets a DOI, and most importantly, every analysis gets a DOI as well that you can reference everywhere. And I think the picture is now about to move to opening the Spectra viewer, so you can actually interact with the Spectra directly in the browser as well, in the repository. Anybody around the world could do this right now. But then, of course, you can also access the original data. So this will be the data as it was received originally from the device, and then including any open formats. So in this case, that's a JCAP. Of course, there are other repositories as well. We operate some other repositories too in NFDI4Chem, and we also work with other repository providers, and we have created this federation of repositories. And within this federation of repository, there's another repository I'd briefly like to highlight to you, which is called NMArchive, which is specifically for NMR data. It's open, it's cloud-based, it's fair, it's consensus-driven, and it is a repository just for NMR data, so raw and processed data. The servers are hosted in Vienna, and it's now also a repository which is recommended also by Angewandte Chemie and also the ACS Journal of Natural Products. So let's have a quick look about the UI. Here you can see a spectra selected. You can see the compound structure, and now NMRium automatically loads. So here there's a COSY being directly interacted with. Further down, there's a whole host of metadata too. So yeah, you can actually interact with all the data directly in the browser. You don't have to download anything. For the molecules, then additional spectra that were measured can be easily accessed and highlighted. You can see what files are associated with the data submission, and then also the license that has been applied to it as well. I'd like to end this talk by talking about reusing NMR data and how we are active in promoting the reuse of NMR data. So if you think about a typical workflow in synthetic chemistry, quite often, especially methods development, chemists will be developing a new chemical reaction. They combine a load of starting materials and reagents together in a reaction, and then afterwards they do a crude NMR. And before they often do this to decide, is it actually worth columning it? And then alongside the crude NMR, they will measure every single one of their starting materials, the reagents, maybe even the solvent as well. So in this case, you can see here, in addition to the crude NMR, they've also then measured 5 additional NMRs, right? And this is an incredible waste of resources and time, because these are commercial materials. And so technically they could just do an overlay with a publicly available spectrum, for example. So our vision is actually that we ingest data from commercial compounds to our repositories, and that actually these data are then mutually exchanged between the repositories, and then chemists in their everyday workflow will go into our repositories to actually interact directly with the data, retrieve the data for their overlays, which then saves them a lot of time and resources. I already mentioned that one of the main benefits is the sustainability aspects. It saves measurements, so it saves helium, NMR solvents, you name it. This will also increase the number of compounds that are in the repositories. They should be very different as well, so this should improve the prediction aspects that Johannes mentioned earlier on in the talk. And from an educational point of view, this is actually really valuable too, because we have, for example, in NMArchive, we'll have very simple molecules fully assigned with all the data, so educators can actually teach the basic principles of NMR spectroscopy directly in the browser without having to pay subscription to a processing software or access to a database. So this would then really also give educators a bit more of a larger toolkit for teaching NMR spectroscopy. So the question is, of course, how do we ingest enough data? And we do have strategies to ingest data. So I'm not going to go into all of them here today, but these are kind of the 5 main areas that we are active in. We are talking to universities that could run teaching labs. So basically, the students would measure a spectrum, assign it, and then publish it. These are typical experiments that happen in teaching labs anyway. They will just measure a spectrum, but they won't necessarily publish it, right? So if they just add the publication aspect to it, we already have researchers, PhD students that are already publishing the NMR data of commercial materials. Anything they buy, they might then just publish. There are also analytical facilities that sit on troves of data. So recently in Mainz, where we are, we are now in the process of uploading a considerable amount of NMR data. We are talking to some commercial vendors as well to provide us with materials or data to put into the repositories. And something that we're really quite proud of as well is that we have some students, or in German, Hiwis. So, for example, in Newcastle in the UK, we have 2 summer students at the moment who are, as part of an 8-week research project, they are measuring NMR data, assigning it, and uploading it to the repository. So it's a great example of international cooperation here as well. If you're interested in contributing data for this project, please do get in touch with us. We appreciate any support, and we're happy to talk to you. And that is now exactly past. So please do follow us, subscribe to us, stay up to date. We have the usual suspects on social media, be it LinkedIn, X, Instagram, YouTube, Blue Sky, Mastodon. We have a comprehensive homepage. We have a newsletter that comes out every 3 months, so please subscribe. And yeah, thank you for your attention.